Welcome back. Today we're going to talk about vector spaces. You've probably run into these in linear algebra before. But a vector space is essentially a collection of things that obeys certain rules and properties. And it turns out that the rules or properties that we're going to define may seem to be pretty simple, but that's the beauty of mathematics. You come up with something simple and it can be very powerful because we can prove things about it. So we're going to first define a vector space, and I apologize, I'm not really good at big script things, as this would be if it was typeset. So S, we're going to say, is a vector space, and it's composed of a set of elements called, surprise, surprise, vectors, and members of a field F called scalars. So by a field here we essentially mean something for which a set of numbers for which multiplication and addition are defined, and they distribute and associate in the manner that we're used to seeing for real numbers. Okay, so the space has rules for adding vectors and multiplying them by scalars. So we have rules for addition and I shouldn't say scalar multiplication. I think multiplication by scalars is more accurate. And these basically come out to, we have vector addition. We just use the regular plus symbol. Combines two vectors into a third. Nothing earth-shattering so far. We've been doing this for a very long time. And scalar multiplication combines a scalar and a vector to produce another vector. So that's easy enough. Let's define some of the rules that apply. Okay, so first, addition. The plus operation obeys these four rules. Obeys rules. So for all x and y that are members of our vector space. So rule number one is x plus y is equal to y plus x. In other words, it's commutative. Fortunately, since I'm stuck here at home with the lockdown, I haven't had much experience with commute lately. It's also associative, as we would normally expect. Third, there is a zero vector, and it's unique. And this works like we thought. X plus 0 is just equal to x for every x in our space. Finally, there is a unique opposite vector, or the concept of a negative vector. Actually, I'm going to write this differently. For each x in our space, there's a unique vector called negative x, such that x plus negative x is equal to 0. So we don't define subtraction per se, but we do define adding a negative number. So we have these four. It's commutative, associative, we have a zero vector, and we have a negative vector. So that's for addition. Now for scalar multiplication, it's also going to follow the same type of rules that we would expect. Let's just put them down here because the first is that for A, B, and F, and X and Y in S, scalar multiplication must obey certain rules. Rule number 1, that A times x plus y is equal to ax plus ay. So that's our distributive property. Two, a plus b times x is equal to ax plus bx, associative. Now, aren't you glad all these work? If they didn't, then we would have to keep track of multiple bizarre properties and mathematics. But here, no, I misnumbered. Yes, that looks better. That's 2. Okay, so for 3, we have an identity in F. So for multiplicative identity in F, which is just general 1, we have 1 times x is equal to x for every x in S. And finally, we're going to have an additive identity also, which is 0. We have 0 times x is just equal to the 0 vector. So, because it's hard to typeset these right, this is the scalar 0, and this is the vector 0. Okay, so everything behaves just like we would expect it to. Nothing new. But these are the basic rules for the mathematics in a vector space. If this is all we had, it wouldn't quite be interesting. So let's keep going on with a few other necessary and interesting properties. And that is, first and foremost, I wish I had room on the previous page because this is really the last thing I wanted to say on this page. And that is S is closed under vector addition and scalar multiplication. So what does this mean? Mathematically, it means if we take any x and y in our vector space, then a times x plus b times y is also in the vector space for every a and b in our field. So this is really a big deal. It essentially means that using these operations, you will always get something that's back in your vector space. And so there are examples where you have sets of numbers or vectors that actually don't obey this rule. So the ones that do are very critical. Sometimes, because of this linearity here, linear combinations are still in the vector space. So sometimes you'll hear this referred to as a linear vector space. Okay, so let's go through a few examples of what vector spaces are and are not. The first, the first one would be Rn. That's where we would have x is equal to some vector x1 through xn, where xi are real. So this is the vectors that you've used before in physics and your linear algebra, matrix algebra class, whatever you've taken. Okay, and in order to have a vector space, this is very important. We can't just have the vectors. We have to have the scalars. So what are the scalars in this case? Well, the scalars would be the real numbers. So let's put that in there. With scalars as real numbers, and the rules using standard multiplication and addition that you've learned previously. So a question for you. What would happen if we had Rn shown here, where x is now equal to a column vector of n real numbers, but the scalars were actually the complex field? Would this be a vector space? The answer is no. The answer is no because it's not closed. So we can certainly define multiplication of x in this case by a complex number, but what we get out using our standard rules is a product that is composed of a vector of complex numbers, which is not in our vector space. Our vector space is made of real numbers. So in that case, because it's not closed, it would not be. But we can define essentially the same thing as above, but with the vectors and the field being complex, but with complex xi and field. I just put scalars. So that works. Okay, so these ones are pretty straightforward. We can get to some strange and interesting ones, or at least further afield. The next would be Galois field. 2 to the n. So here we have we have to define the rest of it. So the scalar field is 0 and 1. So vectors are lists of n bits. So how does this work? Addition would have to be, we have to define that, and it's going to be different now. Addition is modulo 2. So 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, 1 plus 1 is now equal to 0, and this middle one is the same as 1 plus 0. So there we go. So under such a field, our vectors, such a space, our vectors are going to be as defined, a list of binary digits. And so, for example, we could take two vectors, say 1, 1, 0, 1, plus 1, 0, 0, say 0. And get a result there. So while you're considering what that could be, turn to my next page of notes. Okay, so hopefully you looked at this and you said 1 plus 1 is 0. One plus 0 is 1, 0 plus 0 is 0, and 1 plus 0 is 1. So we get some result like that. Okay, so this all works. It's useful in coding and information theory. Another example. I think there are more examples in the class notes that are, the course notes that are posted, but this is most of the useful ones, you might say. Actually, let's do this one. Bounded continuous functions f of t on the interval AB that are real valued. Okay, so in this case we need to once again define our operations and everything else. So vector addition is just going to be pointwise addition of the functions. That's okay, we're used to that. And the scalar multiplication is just multiplying by pointwise. Didn't specify the field. It would be a set of reals. Okay, so if you have two bounded continuous functions and you add those, you're going to get another bounded continuous function. We're going to actually return to this several times, but for now, that's a good example. So here's one that is not a vector space, just for contrast. And that is bounded continuous functions f of t on the interval AB such that the magnitude of f of t is always less than 2. And so this is not because it's not closed. Everything else still works, but you could see that if we were to multiply f of t by, the maximum value in our particular sample f happened to be 1, we multiplied that by 30, we're no longer in that vector space. So this is the main problem here. In fact, most things that look like they might be vector spaces, if they aren't, it's usually because they're not closed. So, vector spaces. We've found that a vector space is what we're used to seeing with vectors, but also we can define them to be something more generic, such as functions on an interval, or these binary vectors. By the way, one thing I'm going to put in here with respect to number 3, or Galois field, and that is, suppose we had x is equal to, say, 1, 0, 1, 0, then we need to have a negative x. Well, in this case, negative x would be 1, 0, 1, 0. It's just the same, because when you add 1 and 1 you get 0, and when you add 0 and 0 you get 0, so that satisfies the definition. Alright, so that's all for this lecture. Next we're going to talk about linear subspaces, and that should be I think a really useful